Look up at the night sky, and you'll see a system of clockwork precision. The planets in our solar system trace smooth, predictable orbits around the Sun, arriving exactly where physics dictates they should be, down to the second. This neighborhood is strictly zoned. Close to the Sun, we find small, dense, rocky worlds. Out in the dark, cold stretches, massive spheres of gas and ice dominate the space. But this peaceful, orderly state is a survivor. It is the quiet aftermath of a chaotic event that tore through space 4.6 billion years ago. We are left to trace the process of how a shapeless, dead cloud of interstellar gas organized itself into the highly structured, life-sustaining system we inhabit today. To understand why our planet exists at all and how it ended up with solid rock and liquid water, we have to rewind the clock. We have to go back to a time before the Sun even existed and watch the physics that architected our home. Our story begins inside a solar nebula. This was a massive, swirling expanse of dead stardust, composed almost entirely of hydrogen and helium gas adrift in a vacuum. For ages, it sat undisturbed in the dark. Then, a massive cosmic disturbance, likely a shockwave from an exploding star, ripped through the nebula. The impact compressed a localized pocket of this gas, forcing it to collapse inward under the weight of its own gravity. This 3D model shows what happens to the material as it falls toward the center. The conservation of angular momentum takes over. The shrinking cloud spins faster, heating the core. That rapid rotation prevents the cloud from falling straight down into a sphere. Instead, centrifugal force flattens the material into a massive, rotating, pancake-like structure called a protoplanetary disk. Right in the center of that disk, the gravitational pull is relentless. It gathers roughly 99.8% of all the available mass in the cloud. Temperatures and pressures hit a threshold where nuclear fusion ignites, and our Sun is born. The young Sun consumed almost everything around it. Yet the entire architecture of our planetary neighborhood, every moon, asteroid, and world, was constructed entirely from the leftover 0.2% of dust scattered out in the surrounding disk. With the young Sun burning in the center, we look out into that flattened ring of remaining gas and debris orbiting around it. Out here, microscopic specks of dust drift and collide. Through simple electrostatic forces, the same static electricity that binds household dust bunnies together, these tiny particles begin to stick. This is the process of accretion. Over millions of years, these tiny clumps steadily gather mass, growing from specks to solid pebbles, and from pebbles into massive boulders. Eventually, these boulders cross a threshold. Once they reach several kilometers wide, their mass is great enough to generate a significant gravitational pull. We now call these massive objects planetesimals. At this scale, gravity takes over as the dominant force of construction, transforming random collisions into a deliberate, sweeping vacuum that pulls in surrounding material to build the planets. We can now address the split between the solar system's small rocky planets and its massive gas giants. Their compositions were determined by their distance from the newborn Sun. This map of the early solar system disk illustrates a thermodynamic boundary known as the frost line. Inside that line, closest to the young Sun, high temperatures vaporized most compounds. Only heavy metals and rocky minerals could survive as solid grains. Because these heavy metals and rocks were rare, the planetesimals remained small and dense. These became the terrestrial planets. Outside the frost line, temperatures plunge, allowing vast quantities of water, methane, and ammonia to freeze into solid ice. With vastly more solid material to sweep up, these outer planetesimals grew fast, forming gargantuan solid cores up to 10 times the mass of Earth. Once a core hits that mass, its gravitational pull is immense. It begins capturing the thick hydrogen and helium gas still lingering in the nebula, swelling into the gas and ice giants we know today. A planet's physical identity, whether it became a habitable rocky world or a sphere of gas, was dictated by its birthplace relative to that single thermal boundary. Even after the primary planets formed, the solar system was not yet stable. It was a chaotic hazard zone, filled with leftover gas, floating dust, and millions of planetesimals zooming through space. The young sun began to produce intense, outward-flowing streams of charged particles, known as the solar wind. This solar wind acted as a cosmic clearing mechanism. It blew the remaining unconsolidated gas out into deep space, cutting off the growth of the gas giants. Meanwhile, the giant outer planets used their gravity to slingshot leftover rocky debris across the solar system. These incoming projectiles crashed violently into the established terrestrial planets during an era known as the Late Heavy Bombardment. This era of collisions cratered the rocky planets and is believed to be the delivery mechanism that deposited oceans of water onto the early Earth. Over billions of years, the orbits cleared, the debris settled, and the space around us quieted into the serene, orderly sky we observe today. Today, every feature of our cosmic neighborhood, from the asteroid belt to the moon's craters and Earth's oceans, is a direct artifact of this 4.6 billion-year-old architectural process. We live in the quiet aftermath of creation.